Imagine a coin spinning in the air. Before it lands, it is neither heads nor tails, but holds the potential for both. Quantum systems, like qubits, behave in a similar fascinating way, existing in a mixture of possibilities all at once. Unlocking the secret to these possibilities involves understanding something called complex amplitudes. Complex amplitudes are the mathematical heart of a qubit state, directly encoding the probability of measuring that qubit in a particular way. Specifically, for a qubit in superposition, its state is described by two complex numbers, alpha and beta. The squared magnitude of each amplitude gives you the probability of measuring the qubit in its corresponding basis state, either 0 or 1. To truly grasp this, let us break it down. First, a complex number is a special kind of number that extends the concept of real numbers by including an imaginary part. It can be thought of as a point in a two-dimensional plane, allowing it to convey both magnitude and phase information simultaneously. This dual nature is profoundly crucial for describing a qubit state in superposition. A qubit in superposition is not just a simple 50-50 mix of zeros and ones. Instead, it also carries precise phase relationships between these potential states, and these phases are vital for quantum computations like interference. The amplitudes, typically denoted as alpha and beta, are these complex numbers that representing both the likelihood and the phase of finding the qubit in the 0 state and the 1 state respectively. For example, if the magnitude of alpha is large, there is a high probability of finding the qubit in the 0 state. The direct relationship between these amplitudes and the measurement probabilities comes from what is known as the Born rule, a cornerstone of quantum mechanics discovered by Max Born. This fundamental rule states that the probability of observing a particular outcome is unequivocally equal to the square of the magnitude of its corresponding complex amplitude. So for the 0 state, the probability is the squared magnitude of alpha, often written as alpha squared absolute value. Similarly, for the 1 state, it is the squared magnitude of beta, or beta squared absolute value. Since we are guaranteed to measure either a 0 or a 1, the sum of these probabilities must always add up to 100%, or exactly 1. This essential principle is called normalization, and it ensures the mathematical consistency of our quantum descriptions. So, what does this mean for understanding qubits? When you see a qubit described by these complex amplitudes, you are essentially looking at its potential future, weighted by probabilities. If you want to know the chances of a measurement yielding a 0, you simply calculate the squared magnitude of its alpha amplitude. Similarly, for a 1, you look at beta. This mathematical framework allows quantum programmers and researchers to precisely predict the outcomes of quantum experiments and design powerful quantum algorithms that leverage these probabilistic behaviors. Without understanding these amplitudes, the behavior of quantum systems would appear random and unpredictable. This concept is beautifully visualized on the Bloch sphere, where the state of a single qubit, including its complex amplitudes, is mapped to a point on the sphere's surface. The distance from the North Pole or South Pole gives a visual representation of the probabilities. Additionally, the phase information, crucial for interference effects in quantum computation, is represented by the angle around the equator. Mastering complex amplitudes is like gaining X-ray vision into the quantum world, allowing you to see the underlying mechanics of entanglement, superposition, and quantum interference. These are not just abstract numbers, they are the gears and levers of quantum mechanics. By understanding how complex amplitudes dictate probability through the Born rule, you gain a fundamental insight into why quantum computers can perform calculations beyond classical limits. It is this probabilistic nature, carefully manipulated through quantum gates that alter these amplitudes and phases, that enables phenomena like quantum parallelism and speedups for specific computational problems. This knowledge empowers you to deconstruct and appreciate the true power behind the quantum revolution.
If quantum tech fascinates you, like, subscribe, and keep exploring with us.